Yeah, dear ladies and gentlemen, now we have a new guest for
Okay.
our symposium interviews. It's a new topic which are very interesting. It's about entropy, and we think we have to invite a person which are always involved in this problem. This is Arieh Ben-Naim. Professor Arieh Ben-Naim is an Israeli professor, which is a professor of physical chemistry since 2003 at the Hebrew University of Jerusalem. And he was always engaged with this problem of entropy, and he has wrote some articles on it. Before we get to this question, dear Arieh, could you introduce yourself?
Most of my research was on the properties of water, the theory of water, statistical mechanics, and recently, well, before I got retired, I did some work on the role of water in some biochemical processes like protein folding, protein-protein association, molecular recognition, and some very important biochemical process to show why water is so important to life in general. I became interested in entropy only after I taught for many years thermodynamics and statistical mechanics, but I became more interested in educational entropy only after my retirement, when I realized the connection between entropy and information theory.
Let me start with some simple question. You have wrote a well-defined, innocent, and powerless concept called inadequately entropy has become almighty, omnipresent, omnipotent, multi-meaning, and monstrous entity, rendering like that was very funny. I love it. Entropy has become far more powerful than any god I can imagine. How have you an idea for this? Could you give a suggestion why this overpowered mighty term turns to entropy?
More than God. I have a whole epilogue on which is more powerful, entropy or God. And actually, there is a whole book by Michael Shermer. A person that I have a lot of respect to him, and I think he's very, very smart. He used to have a column in Scientific American, Michael Shermer. He wrote a whole book discussing the question why God could not create a man or any living system who will live forever. So he asked that question: why God could not create a living
immortality?
Why we cannot live forever? And his answer is because of entropy. So no, and I think it's absurd. It's absurd. I'm not a religious person, but those who believe in God believe that he can do anything he wants. So I don't believe, and I used to believe when I was a child. I grew up in a family, religious family, but at 14 years old, I stopped believing. But anyhow, the whole relationship between entropy and life is completely out. People, forget Einstein's statement that entropy, thermodynamics in general, will be never overthrown. Classical mechanics was revolutionized by relativity, and another revolution by quantum mechanics. However, thermodynamics survived, was not changed. But Einstein emphasized in his statement within the framework of its its validity, of its application or validity. I forgot the exact within. You know, in mathematics, when you prove a theorem, you assume some assumption. You say a function is continuous or differentiate in some interval. So within that intervals, the theorem is valid. And also thermodynamics, classical thermodynamics, all the definitions that I know are well defined within equilibrium system. And that's the main point. Otherwise, Clausius definition cannot be shown to be equivalent to Boltzmann definition. Only if you assume that S, the entropy, is a state function. Now, people forget what is a state function. A state function means if you know the macroscopic state of the system, then entropy is well defined. What does it mean to know the macroscopic system? It's with small number, not all the particles, the location or the velocity of each particle. It means if you know for one component system, the temperature, for example, the pressure or the volume, or the energy, the volume, and the number of particles. 3 or 4, well, depending on the number of components, you have only very few parameters that define the macroscopic system at equilibrium. For each equilibrium system, the entropy is well defined. Now, if I don't know how to define the state of the function, the state of the system, like my body or your body or a body of a fly or any living system, there is no point in talking about the entropy. People talk about the entropy of the whole universe. What does it mean? I mean, it's completely meaningless. You don't know if what is beyond a certain distance. You don't know, even Einstein said, you don't know if the universe is finite or infinite. So no meaning to talk about the entropy of the universe. And there are a lot of popular science books say all kind of beautiful things, pompous things, like what you mentioned, that the entropy doesn't allow God to create a person who will live forever. But there is a book by Sean Carroll, who talked about the entropy of the universe now and the entropy of the universe, the Big Bang, which is a hypothetical case. And then he said that the entropy at the Big Bang gives us information to predict the future. Okay.
Yes. Talking about this point, the entropy of a human body or a fly or what you mentioned. I wanted to ask you to understand better your idea. As far as I know, the subject, it's not controversial that the absolute value of entropy is we cannot measure or say the number of this entropy. But I ask myself, why is it important? Because what we can measure and quantify is the change of the entropy, or you disagree with that? Because in the end, it's thermodynamics, no? So we talk about the change of this entropy or the energy, and the change of the entropy we can measure. Or would you disagree with this as well?
You mean from Clausius or from Boltzmann definition? If you want that Clausius definition and Boltzmann definition will be equivalent in some sense, there is no proof that they are identical. All I'm saying that they are equivalent in the sense that for any system for which you can calculate changes in entropy, you get the same result from Clausius entropy and from Boltzmann entropy, as well from the entropy that I derived from the Shannon measure. But leave that. Some people don't like it. I think it's the best definition. Anyhow, now how you talk about changes in entropy, I say that for living system, entropy is not even definable. You cannot define it. So there is no meaning to talk about changes in entropy. Maybe you think about ds equals dq over t. But this is for a well-defined system at equilibrium with a specified temperature. So that's the entropy that goes from the bath, the thermal bath, into the system. But you don't know if the system is my body. You don't know my entropy, and you don't know. You cannot tell the change in the entropy. So there is no point of talking about it. Let me tell you one more thing about the bath. There is a book by Atkins, The 4 Laws That Drive the Universe. Now, you know, the second law that entropy always increases in a spontaneous process is valid for an isolated system. You know, isolated system means constant energy, constant volume, and constant number of particles. In other words, completely isolated. There is no interactions with all the worlds. Now for this system, the entropy, whenever you remove some constraint or some partition, like in expansion or in mixing, entropy will increase. This is not true for any system. Like if you take a system in a thermal bath, okay. Now how you go from this principle for entropy increases into Gibbs energy or Helmholtz energy going down, you assume that your system is in a thermal bath and the whole thermal bath is isolated. Now you apply to the first law on the thermal bath with the system, and then you derive for the system which is at constant temperature. If it's at constant temperature and volume, that for any spontaneous process at T and V and N constant, the Helmholtz energy will go down. If the pressure and temperature and number of particles are constants, then the Gibbs energy will go down. But now remember, the trick is to go from the entropy principle or the entropy, what they call the entropy formulation of the second law, into Gibbs formulation of the second law or Helmholtz. You take your system and put it in a thermal bath or in a bath which has a constant temperature and pressure. But the whole bath, which is much bigger than the system, should be isolated. Now, what Atkins does, and that's a big error, he forget about it, and he replaced the whole bath by the whole universe. And then he said, in the universe, the entropy increased. And that's unfortunately also a mistake that was done by Calcius himself. Calcius said that the entropy of the universe always increases. And I think that's meaningless. And it's understood that Clausius had no idea what entropy means on a molecular level. This came much later after Boltzmann. And now I think it's much better known after information theory. It's even more, I think, more intuitively understood.
Can I ask one more question just to understand
sure.
the problem with the measuring of the change, because we have a similar problem measuring the change of the internal energy of an object. No, this is the same principle. We have also the internal energy of an object. We don't know the value, the absolute value.
The internal unknown. The internal energy.
Internal energy,
internal
the energy, not the entropy. But I see the problem is similar. Yeah, you have
yes, of course. I agree.
have an unknown internal energy, but that you cannot know. But you measure the change, measuring the heat that's given from the object or from the system to the outside. So would you consider that we have the same problem here as well with the entropy, or is it different for you?
Well, I think with the internal energy, you have the first law that if you do some work or you transfer heat, you assume that both of them change, increase or decrease the internal energy, and you are referring to the absolute internal energy, which must be defined relative to some reference state, compared to some reference state, right? And that's the same with the entropy. If you assume, which is not always true, I don't know, it is called the third law. You assume that all the system at zero temperature the entropy will go to zero. But we know many exceptions that the entropy there is some degeneracy, or there is some zero entropy, even if theoretically you cannot reach zero, absolute zero. However, one can show that in most cases, difference in entropy for any reaction or any process goes to zero when you come very, let's say, as close as possible to the absolute temperature. The third law gives you the entropy at zero, but all we know is actually about change differences for a specific process, the change in entropy, how they change when you get to zero, and that becomes smaller and smaller. And of course, for many systems, like to take argon or simple liquids, you can show that if you measure the heat capacity, you know how you do the absolute entropy. You have to integrate from zero or nearly as much as low as possible up to the temperature that you want. You integrate Cp or Cv, the heat capacity, over T dt, right? You get the entropy, and you compare it with what you calculate from Boltzmann, S equals K log W, or from Gibbs entropy, which is derived from the Boltzmann entropy. You get the same results. However, we know that there are exceptions, and water, on which I worked many years, water is one exception. There is zero. There is entropy even if you go at very low temperatures, because of the location of the hydrogens on each hydrogen bond in ice. The hydrogen can be either close to one oxygen or to the other. There is a hydrogen bond, OHO.
Yeah.
And the whole structure of water is OHO with different structure. The regular ice is some kind of hexagonals. In any case, the H can be in two positions, and there is also quantum mechanical tunneling effect between the two positions of the hydrogen between the two oxygens. So this causes some kind of degeneracy, and I forgot who was it. Maybe Pauling. I think Pauling, Linus Pauling. I think it was Linus who first calculated the entropy of water at very low temperature, at zero temperature. I think it was Pauling. I forgot it. But there are other cases like NO that can be NO in a crystal and ON, different. So each one has two different positions. So the calculation is much simpler. So this is 2 to the power of n, whereas in water it's a little more complicated.
Arieh, but when we come to the starting point, more speaking a little bit general about your thoughts about entropy. When I understand you don't neglect the state of thermodynamic second laws. You accept that it exists. This point that there are playing a role of it, and you've mentioned that there is an over categorization because the term entropy was used in some fields which have nothing to do with entropy. Yeah,
right.
Is it right? Okay, so you say the Shannon measure information theory is the over topic from the thermodynamics second law. Is it right? Yeah, and over that we can talk about the general information theory, which put all these things together. But your point is more. You say that entropy is much better to explain with the Shannon measure information. Yeah, it's right, huh?
I think there are three definitions. I think well-defined quantities that are called entropy. One is Clausius, which is only for small change. It's not. Yeah. Clausius never defined entropy itself. Clausius, with the third law, makes a definition of entropy. Then there is Boltzmann, and then there is the one that is based on Shannon. Yeah. Now, all I'm saying, there is no proof that all these three, any two of them, are equivalent in absolute sense. There is no proof. In fact, every definition looks from a completely different thing. However, from our experience, you know that entropy is not easy to calculate for liquids, for some solids, and not to speak about animals, impossible. But even for water or for a mixture of hydrofluoric acid, when the interactions are very strong, it's very difficult to calculate the entropy. But for all the systems for which we can calculate the entropy change, all agree, and most of the systems are either ideal gases, mixtures of ideal gases, where there are no interactions or very little interactions, like small variation for small deviation from ideal gases, or for perfect solids, when you have perfect order and you can calculate for example, in metals, in mixtures, you can calculate the number of configurations, and that's what Boltzmann did. And you get the same result from either Boltzmann or Shannon or from Clausius. So in this sense, I'm saying it's equivalent, but with some reservations only for those systems for which we can calculate the entropy. If you will come someone will come with very complicated system, it might not. I don't know. There is no proof that you cannot derive the Boltzmann from the Clausius. You cannot derive the entropy from Boltzmann, from the Shannon measure. It's completely different sources. Somehow they give the same results. For ideal gas, you get the same result. This is it's called the Sackur-Tetrode equation for ideal gas or for mixtures of ideal gases. And this is the best thing that we know for any, not only ideal gases, reactions, all chemical reactions in ideal gases. When you come to liquids, is less certain. For perfect solids, then again, you can calculate the entropy and entropy change for different alloys or mixtures of metals.
When I understand you right, the core of your critics is that entropy always used with a causality. You know what I mean? Entropy.
Well, no, I don't agree with that.
Yeah,
I know a lot of people say that entropy is the cause.
Yeah,
the cause of any spontaneous process. I think the real cause of a spontaneous process, I think is the tendency to go to a more probable state.
Yeah,
and the entropy change is a result of the process, not a cause.
Yes.
This I wrote in details in my book, Entropy: The Greatest Blunder in the History of Science. This is the most recent book that I wrote on entropy, where I criticize all the interpretations like order or a measure of spreading, probability, even information. You know, this is important. In information theory, I always emphasize, and even Shannon himself, Shannon measure of information is a well-defined quantity in probability theory. It is not information in general. Information in general is a very huge concept. Not every information can be measured. It's only information which you give as a signal, and that's what Shannon was interested. He was interested in messages that you send by letters. And if I say by letters, and each letter, each letter has a probability, right? Like E is very probable, and I think J and Q and some other letters are very improbable. So if you know the probability of the letters in a specific language, if I give you a message in English, you can write the Shannon measure of information. Now, if I give you the same, like what is the weather in New York today? If I give you this in Deutschland, in Deutsch, or in Spanish, or in Hebrew, or English, the distribution of letters will be different, and the information is the same, but the Shannon measure is different, completely different. And on the other hand, you can show that I give examples in my book. I have a book on information theory. If I tell you that that Bob loved Linda, okay, so I can write the Shannon measure of this. Bob loves Linda, okay. This is information. I give you information, and you can write down according to the letters. If I said Linda loves Bob, That's a different information, right? Yeah. Linda loves Bob. It's different from Bob loves this. Okay, now the Shannon measure is exactly the same. Now, if I say love Linda Bob, what does it mean? Love Linda Bob. Love Bob Linda. It's meaningless, right? It's not like what we said before. Bob loves Linda or Linda loves Bob. These are two informations, different informations, which have the same Shannon measure. In terms of communication, you know, the work of Shannon originally was a mathematical theory of communication, because he was interested in transmitting information with lowest cost and high fidelity in encoding and decoding of information. And he emphasized it has nothing to do with the meaning of information. If I give you all the letters, we are going too much in information theory. If I give you all the letters in Bob loves Linda, and I mix up all the letters, I can do many sequences. All of them have exactly the same channel, because to transmit them by Morse or by any code is the same. It costs the same thing in communication line. However, the meaning, it could have meaning, it could have different meaning, it could be also meaningless. So the information of the message is irrelevant to the measure of information. It's important. While I'm saying this, because people say that that entropy is a measure of its information.
I have another question. Yeah, you've mentioned there is a mistake when we mixed up entropy with probability.
Right.
Yeah. Can you explain it a little bit clearer?
Yes. And this is very important. It's very subtle. Look, entropy is not probability. That's absolute. Now, there is a relationship between ratio of probabilities and difference in entropy. Now, again, this has to be clarified. Un minuto, por favor. Un minuto.
Okay, no problem.
Sin problema, sin problema.
You can make
the lecture that I gave. Can you see that? Can you see that? Can you see that?
Yeah. I can see it. Yeah.
Okay. I will go. I want to show you one thing here. This is how I explain the relationship between information theory and the 20 question game. I choose a person, and you have to find out which is the number, which is the person, or I have some, you do it with children. This game, you see the game. I'm thinking of something, and you have to find out. But let me go to your question. Un minuto.
Sin problema. Una cerveza más, por favor.
Can you see this?
Yeah.
Sure.
Yeah.
Let me explain. A is an isolated system with some partitions where there are N1, N2, N3 particles, but the whole thing is isolated. Can you see?
Mm-hmm.
Now let me explain. A is an isolated system divided into subsystems with different number of particles, okay?
Mm-hmm.
Now B, but it's at the moment I remove all the partitions, okay?
Mm-hmm.
And C is the equilibrium system. Okay, think of simpler than that. Instead of many subsystems, one box with one partition. All the gas are in the lower part, and I remove the partition and it will expand, right?
Yeah.
Okay. Now A is the initial state where all the gas are in volume V, in volume V initially. C, the last one, is when I remove and you get the equilibrium state, where all the same particles are in the 2V. Okay? Now B is a special system where I just removed the partition. It didn't start to expand. So all the particles are down, but it's non-equilibrium state, right? It's not. It will start to expand. Okay. What I want to say is that the entropy is defined in the state A and in the state C, only at equilibrium A and C. Now, look, the difference, delta S, in this case, in this expansion, is R log 2. You know that? R log 2, this is the expansion of ideal gas from volume V into volume 2V. The explanation in terms of Boltzmann is the number of states increased from V to 2V, the number of states. In terms of Shannon measure, I knew that each particle was in V. After the expansion, I don't know, is it in the upper part or in the lower part? So I lost 1 bit of information for each particle. For altogether is R, which is the Boltzmann constant, Kn log 2. Log 2 is the amount of information per one question. 1 bit of information. Okay. Now, very important, the connection with probability. The difference between the probability in the last equilibrium and the beginning is R log 2, right? R or Kn, or the number of particles, K Boltzmann constant, or R the gas constant, log 2. Now, the difference between A and C is well defined, okay? Now, the probability of the state A is 1, because that's equilibrium. That's the probability of the state. The probability of the state C is also 1. So the difference is not the probability ratio between the two, because this is 1 and this is 1. The probability of A is 1. The probability of C is also 1. However, there is a difference, the difference in probability between the state C, S of C, and S of A is the ratio of the probability in C, which is 1, and the probability in state B. You see, the question is, what is the probability that when you have the equilibrium, the final equilibrium state, C, there is a very small probability that the system will, all the particles will go into one volume. I have here, I did simulation here. I don't know if I can show you that.
Yeah.
So this is the initial state, A. Well, it doesn't show A. Yeah, no, that's the notation is different. Let me show you. This is the for 4 particles. When you expand it, there is a probability that all the particles will come here, right? So the ratio of the probability of the final state and the probability of that all the particles will be in the initial state is related to e to the difference in the entropies. However, the probability that all the particles will be here, but without the partition, because it will not come spontaneously. You have to put it. So let me again explain. There is a difference. There is a correlation between the ratio of the probabilities of the 2 states and the difference in the entropy of the 2 states. But when I say initial and final, I mean 2 different things. For the entropy, I mean the initial A at equilibrium and the final C at equilibrium. When I talk about the probability, I talk about the final C and the state B as initial. Initial in the sense that after removing the partition. So this is a subtle point because there is no, you cannot talk about when you are in the final state C, you cannot get into A, because to get into A you have to get spontaneously with the partition inside. You have to put the partition, but you can get into B. You can get all the particles in volume, half volume or quarter, or whatever you want. It's very improbable. It's one. The probability is 1/2 to the power of n. And if n is 1,000, this is very, very small. If n is Avogadro number, you can say never. It will never occur.
Arieh, but this is a big point when you mentioned this, because there's a great group which thinks that there is a irreversibility of processes. It's okay. It's not a great probability that someone when I throw this downstairs, it jump up from itself. Okay, there is a little bit probability that it could be, but in this point, you have to make it a little bit weaker. Yeah, you have to say, okay, it's not very probable that some things which are thrown up this dishes jump from itself upstairs, but it could be there is a little, but there is a probability. Is it right?
That's right. That's exactly what Boltzmann said. He said that it is not impossible, it's improbable. Very, very high improbability. It's almost zero. Now, one more important thing, why one confuses entropy with time. And I don't know if you know that there is a book, I forgot the name of the author, that actually equates, say, entropy equals the error of time. I forgot the name. And this is completely nonsense. Let me say why this is not true. I'm saying, first of all, time can never decrease. You agree with that?
Yeah.
Why? Why? Because any way that we don't have really definition of time, but we have ways of measuring time. All the way that ever in the history that we measure time was by measuring some periodic phenomena. In the old time, the rotation of the earth or the rise and set of the sun. So every time it repeats, you say a day pass, or later you had a crystal, so you have the oscillation of the crystal. Now in the atomic, you have a vibration of the electromagnetic. So whenever you have, you count the number of periods or the number of cycles that pass. This number can never decrease. The number, like if I tell you what is the number, the total number of books that ever were published, this number can only increase. It can never decrease. Maybe if no one will write books or all the people will die, there will be no more increase, okay? But as long as people write books, the total number of books published can always increase. Even if all the book will be burned, still it cannot be reduced. In the same sense, when we count time, we count how many turns the Earth or the Earth around the Sun or whatever. You know, in Argentina, when I spent a year in Argentina, they said that they measured the time in terms of the cigarettes. How many cigarettes I can smoke? He said, after 2 cigarettes, I will come. So, you know, I don't know how, I don't smoke, so I don't know how time, but anyhow, so in any case, time can never decrease in absolute sense, never can decrease. I don't know if it will, if the whole world will freeze one day, maybe there is no meaning to time, because if there is no way of measuring time, maybe suppose the whole world will be frozen. Okay, so I think that time will stop. Okay, now people confuse this time with irreversible process, like the expansion. They said the expansion from V to 2V will always go in one direction. It will never decrease. The particles will never go back to the initial state. This never is not like in time, is not absolute. This is because the particles there are many particles. If you take 10 particles and expand them, there will be one in a month or something. You will see all the particles in the bottom, or all the particles in the upper part. However, there is no sense that this is a one direction system. For n particles, n of the order of 10 to the 23, you know, it's a huge number. It will always increase. It will never decrease, not in our lifetime, not in the lifetime of the universe and many lifetimes of the universe, but still, it's not absolute never. So it's a different never than the mathematical never of the time that can never decrease. So in this sense, I think the confusion is between, you know, the irreversible process is related to change in entropy. And people say the change in entropy is the direction of time. I think it has nothing to do, and it doesn't follow from any of the definitions of entropy.
Ari,
Claudius,
as far as I understood, the entropy is sometimes used to explain our sensation that time is passing, you know, the time arrow. And if it's not done by entropy, do you have another explanation for this sensation that time is always going to one direction for our sensation of it?
I agree with that sensation. Everyone has that. But entropy, not only that, you know, there is a lot of research. I wrote a book, it's called Time for Smart Kids. There is, I summarize the research of others. You know, at low age, you have a feeling that time is running much faster. When you are younger, times go slower. Also, when you are in tension or you are in stress, you feel the time goes very slow and you feel like a year passed. When you are happy and you are enjoy yourself, you have a feel. So it's not only the time increases, is also the rate of change is a very, very subjective feeling that you have a feeling that it goes quicker or slower depending on your mood, on your age, or your activity and so on. But in any case, I can claim definitely that entropy has absolutely nothing to do with time. That's my view, and unfortunately, people still believe that there is a relationship. What can I do?
Yeah, I just wanted to comment on the connection between entropy and the living organism, or entropy and life. And I think the major problem is that you cannot even conceptualize what entropy in a living organism means. And because you cannot come up with a concept, you cannot even measure it. So the people who claim that, for example, an organism has to decrease its entropy, they cannot make the jump from a, let's say, pure philosophical or metaphysical argument to a scientific one. Because in the first place, you don't have a clear concept of what you mean by entropy in a living organism. And because you don't have a clear concept, you cannot even measure it. But
I agree.
Yeah, but
absolutely.
But you can measure the change of the entropy.
No, how you can measure the change if you cannot, if it's not even definable for it's not defined. No, I'm not talking about measuring absolute. I'm talking how you define the entropy of a living system. How you define it? By which definition? You know that the total number of states of the system. Like Atkins, he said that all our thinking and all our feelings and all our creation of artistic, are a result of the second law of increasing entropy. I think I'm sorry to say, I think it's totally stupid to say that, because how you define the entropy of your brain, of your system, of the thinking. We don't know yet how the brain completely works. We know some, but it's not a well-defined system. So, and certainly we cannot.
Yeah, I mean, you cannot even measure a complete organism. The question is, what do you want to measure, and what is your scientific tool? Yeah, so what is your technique to measure a complete organism? And that, of course, is impossible. So what you could do, you could only measure parts of the organism, like any science does. But even
not
for parts, I agree.
If you isolated some well-defined reactions like metabolism, in experiment, in well-defined temperature and pressure, you take it out. Of course, we know a lot of metabolism, and you have a lot of biochemistry that we know, but this is studied in vitro, in the laboratory. But we don't know anything about entropy of the whole living system.
But Ari, this was my question.
I mean,
before.
it's not.
Ari, this was my question before.
Yeah.
But what is the difference to the inner energy, to the internal energy of a system? Because we have the same problem there. We don't have the exact number, but of course we can measure the change of the internal energy. And from my point of view, it's the same with entropy. It's exactly the same.
Well, I think in internal energy, I'm not sure that you can measure of a living system, how you measure the change in the internal energy when you are thinking, or when you think, or you compose in your brain music. Can you even think about the change in internal energy of your thinking or your feelings? I doubt the material body, but if you talk about the whole system with the mental, like Atkins that was I was attacking Atkins. I think it's meaningless, even internal or not internal. So the temperature. What is the temperature of your feeling? I can measure my temperature of the body. Okay, and to some extent, it is the same in all the body. Maybe could be different, small differences. But what's the temperature, or what is the volume of my thoughts or my feelings? I mean, what are these physical quantities? And certainly, I don't know what has to do with entropy. So
yeah, I really, Ari, I really love this question. I really love it. I didn't think that we were going to the qualia problem today, but but my thoughts were about the body as a material system. So if you have a material point of view, you would say, maybe it's not my point of view, but you would say, okay, when you have thoughts, something happens in your brains, some reactions, and these reactions produce heat, and you can measure the heat that's coming out of the brain. So
okay.
You can,
yeah, okay. So you can
heat.
measure it, and if you pressure on my skin, if you measure and my skin and you do work, I agree that in some sense you can say that this work was translated into internal energy in the body.
Yeah.
But I'm talking about the internal energy of the whole living system, including the brain, like what Atkins said. He said that the feelings and our thought and our creation of art all are changing in entropy. And I think that's true. Really meaningless. I don't know what to say. So I agree that in some sense, if you heat the body, you transfer from a bath at temperature T, it's reasonable that the change in the entropy of that part of the system that it goes, it's the same. It's minus dq over T. Sorry, of the bath, it's minus dq and of the system. But if you talk about the whole body, including the brain, or many other things that we don't know how they operate, then I think it loses its meaning. There are some degrees of freedom that we don't understand them in terms of physical quantities, like volume, even volume. What is the volume change when I think? I don't know.
So the brain and the thought are making the difference. Because it's not always so easy when you think of a beautiful woman, the temperature goes up, but it's not always that easy, no?
Not always, and not the same for every man. I don't know. Well, anyhow, I have objection to use of entropy for two main things, one for living systems and one for the entire universe. Again, it's the entire universe is not well defined yet, and I cannot talk about the internal energy of the entire world. I cannot talk the volume of the entire universe, and of course not the entropy, and certainly not about talking about that entropy always in the universe always changes. I think this is a meaningless statement that was done by Clausius himself. You can say it's reasonable to say that the universe is going to a more probable state. Again, is that true to say about human beings? That what you do because this is more probable? I'm not sure that's true. I might do something which is not probable. You know, what I do out of what we call free will, it's not a random thing that according, you know, it's meaningless. So unless there is some other quick questions that I thought.
I have a last question, perhaps.
Yeah.
I'm interested in the question why we use entropy always for some mysterious things which we can't explain. I think it's a little bit similar to emergence. Do you know the term emergence? It's always it comes when we have an answer for any problem. We say, oh, there emerge. The
I know. Even think about that our thinking and feelings are emergent phenomena, actually electrical communication between the neurons.
Do you think it's a similar strategy behind it? It's a similar.
So I think entropy, because it was so much misused and interpreted in so many ways, that it confused a lot of people, and that's why people like Green in his book The Magnificent Universe said that it is the most mysterious quantity. I don't think it's mysterious. I think it's a well-defined, well-interpreted. Unfortunately, people say it's mysterious either because they don't understand it or because they heard that it has, you know, very power, like what you started with, that it's more powerful than God. And of course, if it's more powerful than God, that it's very mysterious. And God itself is mysterious. So I don't think entropy is mysterious. I think it's a well-defined, well-interpreted, and a lot of people, unfortunately, misuse it and misinterpret it.
Okay.
What can I do?
Okay.
C'est la vie.
C'est la vie.
Oui. ¿Hablas español?
Señor.
¿Hablas español?
Ha sido un placer.
Y a mí también.
It was great to have you, Ari.
Yo estuve un año en Argentina, un año en Chile y 2 años en España.
Ah, 2 años en España.
En Burgos, en la Universidad de Burgos.
Ah, en Burgos. ¿Has comido cordero?
¿Cómo?
¿Has comido cordero? Did you eat lamb? Burgos is very well known for lamb. Cordero.
Okay, did you record all this?
No, we'll be cutting out.